It was in 1976 when the Institute of Plasma Physics and Laser Microfusion began its activity on the initiative of Professor Sylwester Kaliski, the then Minister of Science, Higher Education and Technology. He was previously the rector of the Military University of Technology, where the first lasers in Poland were created in the early 60s. Plasma concentrators, developed at the Institute of Nuclear Research in Świerk, were the second contribution to establishing the IPPLM. Both of these devices, lasers and concentrators, are capable of producing hot hydrogen plasma. It is so hot that the nuclei of the hydrogen isotopes, deuterium and tritium, can merge, imitating the process of thermonuclear fusion that takes place at the center of the Sun. In 1973, the first experiment using concentrated laser energy was carried out. It was confirmed that it is possible to obtain neutrons from nuclear fusion. The scientists from the Military University of Technology and the Institute for Nuclear Research joined the experiment. In 1975, a combined focus laser experiment was performed at the MUT. It was this experiment that became the foundation stone of the IPPLM, which started its activities a year later. In the 90s, the biggest plasma focus device in Europe was installed in the IPPLM. In this kind of systems, hot plasma is generated by high-voltage electric discharge. The discharge takes place between cylindrical electrodes. The accelerated plasma layer collapses at the end of the electrodes, creating a focus which becomes a source of neutrons, ion and electron beams, as well as X-ray radiation. It is these particles and waves that can find their application in many fields of science and technology. The Institute is exploring this field with the support of funds of the International Atomic Energy Agency and the Ministry of Science and Higher Education. Plasma focus is a plasma device of interest to scientists from all over the world, gathered in the International Center of Dense Magnetized Plasma, which has been operating within the structure of the IPPLM since 1999. It was established under the auspices of UNESCO. The technology of plasma focus generators has also found the industrial applications, such as generating current pulses which stimulate lightning strikes. In this way, the laboratory of simulated atmospheric discharges was established and to this day provides its services to test the resistance of various devices, including avionics, to lightning discharges. Lasers are an invention for which the American Charles Townes and the Russians Alexander Prokhorov and Nikolai Basov received the Nobel Prize in 1964. Nikolai Basov worked at the Lebedev Physical Institute in Moscow and studied the application of lasers for nuclear fusion. In the 70s and 80s, the IPPLM cooperated with the Lebedev Institute, conducting experiments in Moscow on the Kalmar and Delphin systems, and in the IPPLM taking advantage of the systems built at the MUT. Currently, scientists from the IPPLM are studying laser plasma in a number of foreign centers, in Prague on the PULSE system, in France and in Great Britain. In the future, also on installations in the Czech Republic, Romania and Hungary, where high-power lasers are developed as part of the European infrastructure called ELI, Extreme Light Infrastructure. In the IPPLM, the high-power laser laboratory equipped with a 10 terawatt laser has been created. It is in this laboratory that research is carried out with the participation of European scientists, which is our contribution to the development of the concept of inertial confinement fusion produced by lasers. In 2004, Poland joined the European Union and became a member of both communities. It was important for the Institute to join the Euratom community. The Euratom community has been conducting research for over 50 years to build a power plant operating on a completely new physical basis, such as nuclear fusion, which is the source of stars' energy, including our Sun. Nuclear fusion is based on joining of hydrogen nuclei, or the nuclei of its isotopes. As a result, helium nuclei are formed, and a small difference in the mass of helium and the mass of hydrogen nuclei is released in the form of neutron kinetic energy, and helium ions to a lesser extent. In the Sun, 4 hydrogen nuclei merge, On Earth, the more promising thermonuclear reaction is a combination of heavier isotopes, deuterium and tritium. These reactions occur at a very high temperature between 10 and 20 million degrees in the Sun, several hundred million degrees on Earth. At this temperature, matter is in a state of plasma, hot ionized gas. In the future, nuclear fusion may become the basis for a new type of thermonuclear power plant. Electricity will be generated there in a safe, environmentally friendly, and very efficient way. It is the most effective source of usable energy in the universe. Together with green renewable energy, it will become the basis of zero-emission energy in the future. Research to confine nuclear fusion is carried out all over the world. The goal, a thermonuclear power plant, can only be achieved through the cooperation of all mankind. No single country will ever accomplish it on its own. Poland, represented by the IPPLM, has its share in this venture to the extent of our capabilities and experience gained throughout nearly 50 years of research on plasma physics and nuclear fusion. In 2005, the IPPLM became the leader and coordinator of a nationwide research network called the Euratom IPPLM Association. Professor Andrzej Gałkowski became the creator and the first head of the association. In 2014, the association was transformed into the Scientific and Industrial Center New Energy Technologies. The center consists of research teams from 9 universities, 4 research institutes, and 2 institutes of the Polish Academy of Sciences, as well as the Wrocław Technology Park. The IPPLM represents the center in the European consortium, Microfusion, which coordinates activities within the community. The consortium's experimental research work focuses primarily on tokamak devices. Another device from the magnetically confined plasma group is a stellarator. Institute's scientific teams implement several joint projects of the Microfusion consortium regarding fusion research on large toroidal systems, tokamaks and stellarators. In experimental works, the devices developed and tested at the Institute are applied. The Wendelstein 7X stellarator, located in Greifswald, Germany, is a global fusion device with the IPPLM researchers involved in its operation. We have participated in the project to design, develop, and operate the X-ray diagnostics for Wendelstein 7X for more than 10 years. The first system is a pulse height analysis diagnostic, which works with the semiconductor detectors, PHA system. The PHA system was one of a few diagnostics operating during the first experimental campaign of the Wendelstein 7X stellarator at the end of 2015.
There was the plasma.
Another diagnostics under development with the participation of the IPPLM and the Opole University researchers is the spectrometer for light impurities observation called the CO monitor, short for carbon and oxygen. The information obtained will allow to assess the condition of plasma in the stellarator and monitor its composition. A stellarator is a concept with advantages from the point of view of continuous operation of future thermonuclear power plant. Currently, however, the concept that promises the most for the industrial confinement of fusion is a tokamak, toroidal chamber with magnetic coils, hence the English name being an acronym from its Russian equivalent. Plasma in such a device is kept away from the chamber walls by means of the configuration of the magnetic fields. JET is the world's largest experimental tokamak, currently the only one in which plasma of a mixture of deuterium and tritium can be generated. JET was built in England near Oxford. It is the property of Euratom community and therefore of Poland as well. Polish scientists, mainly from the IPPLM and the National Center for Nuclear Research, make extensive use of the opportunities of experiments conducted at JET. Researchers from the IPPLM have participating in experimental campaigns on the JET tokamak for many years. These works refer to the analysis of experimental data calibration and the development of new diagnostics and plasma modeling. In addition, Polish scientists participated in the calibration of the neutron diagnostics at the JET tokamak performed with the use of a 14 megaelectron-volt neutron generator. Currently, 2 GEM gaseous electron multiplier detectors, developed by the team of researchers from the IPPLM Warsaw University of Technology and the University of Warsaw, are used on the JET tokamak. This diagnostics is one of the key ones as it provides information on the plasma impurity density, electron temperature, or plasma rotation. The knowledge and experience acquired during the implementation of the project for JET allowed to implement another project, this time for the West Tokamak located in Cadarache, France. In this case, researchers from the IPPLM together with the Warsaw University of Technology participated in the development of a soft X-ray tomography system based on the GEM detectors for monitoring of tungsten transport in plasma. One of the important issues to implement fusion on Earth is the selection of materials forming the elements of the first wall of thermonuclear reactors. This is not a trivial issue. One needs to find a material which, in one hand, will not contaminate plasma, on the other, it will be resistant to extremely high temperatures. This is why plasma wall interaction studies are an important element of the Eurofusion program. For many years, the Institute has been implementing the project aimed at applying LIBS diagnostics, laser-induced breakdown spectroscopy, to study fuel retention in the composition of examined samples. This diagnostics was tested on the Italian tokamak FTU in cooperation with the Enea Frascati. The efforts of 7 world powers, the Euratom community, Japan, USA, South Korea, Russia, China, and India, support the construction of the next-generation thermonuclear reactor, ITER, which means road in Latin, in southern France in Cadarache near Marseille. This will be the last experimental reactor on the way to a thermonuclear power plant. ITER aims to show that nuclear fusion electrical energy is feasible on an industrial scale. ITER's successor, DEMO, will be a prototype thermonuclear power plant. Poland, including the IPPLM through the involvement in the Eurofusion program, participates in works related to the construction of the reactor and preparation of experimental campaigns on the ITER tokamak. In recent years, the Laboratory of Plasma Space Propulsion has been created in the IPPLM from scratch. The laboratory was equipped with a chamber simulating space vacuum, thrust balance, and ion diagnostics. Plasma controllers can be used to correct the orbit of small satellites orbiting the Earth. They use the conversion of electricity into kinetic energy of plasma particles. This method is more effective than the method applying chemical fuel energy. The IPPLM tests pulsed ablation thrusters and Hall thrusters of continuous operation. In the Hall thrusters designed in the laboratory, the working gas is krypton, much cheaper than xenon used previously. The IPPLM cooperates with the European Space Agency, which partly finances this research. Every 2 years, the IPPLM organizes the International Summer School of Plasma Physics for young scientists in Kudowa-Zdrój. Topics include plasma physics, nuclear fusion research, plasma experiments together with plasma diagnostics. Every 2 years, it organizes the International Conference Plasma, dealing with plasma physics and nuclear fusion. Every year, it participates in picnics and festivals promoting science. Together with the Go Theatre, it organizes artistic and scientific workshops for the Institute of Metaphysics, dealing with imagination and creation, science and art, combined with visits to the IPPLM laboratories and meetings with scientists.
Woda, powietrze i